Hi, I'm an old guy and I do maths, and today we're looking at a further example of differential graphs. This one's involving a cubic, and what we're going to do is we're going to take a look at its differentials graph and see again what it can and cannot tell us. Now, I've done this previously with a quadratic and the resulting linear graph. Now we're going to see a little bit more. Okay, so what have we got? Well, here's our cubic, x cubed plus 8x squared plus 9x minus 18. Trust me, these are the solutions. This is it very roughly graphed, just sketched. This is the differential. 3x squared plus 16x plus 9. And these are its solutions. Trust me, you don't want to see me do this. It's just going to soak up a lot of time. It's negative 8 plus or minus root 37 on 3. That is where this graph hits the x-axis. So let's have a look at that graph and compare it to the graph of the cubic from which the function that gave us this comes. What does it tell us? Well, it tells us quite a few things, but it doesn't tell us a lot of what people tend to take from it. People get really confused about the graphs of differentials, and it's not uncommon to see a question posed in the form of, here is the graph of a differential. What could the original graph look like? Not what does the original graph look like, but what could the original graph look like? Because no matter how much information we have about this, we're still missing some vital information. An example of that vital information would be where this thing crosses the y-axis. There's not really anything here to tell us that. If we figured out what the equation of this function, of this graph were, we would still be in the position of having to integrate it, having to anti-differentiate it, and we would wind up with something like this. X cubed plus 8x squared plus 9x plus c. We wouldn't know what that is. And that's quite important. So, it doesn't tell us the full equation of our graph. What does it tell us? Right. Well, hopefully I've drawn this accurately enough, sketched it accurately enough. Well, not quite actually, but what you can see is that if I join these 2 points like this, where this is equal to 0 is the turning point of this. There and there. And if you think about it just for a moment, it makes sense. This is a graph of the gradient of this function. This function has a positive gradient above negative 8 plus root 37 on 3 on the x-axis. That is where this graph breaks the x-axis and has positive y values. Between negative 8 plus root 37 on 3 and negative 8 minus root 37 on 3, this graph has a negative gradient. And the values of the differential graph are negative. Back beyond this point here on this graph, the gradient is positive. It has come through the x-axis, and the y values, not the gradient, do not mistake this for the gradient. It is the value of the gradient. That's really important. It has broken through the x-axis at this point, and the gradient all the way back to negative infinity will be positive. So it's positive here, negative here, positive here, positive here, negative here, positive here. But this is a gradient, this is the graph of the gradient value. And at this point and this point, we have a gradient of 0 reflected in a y value of 0. That is how you read the graph of the differential of a cubic. And it goes without saying, but I'll say it, it is the graph of a quadratic, because when you differentiate, you move down by one order. Okay, well, I hope you found that useful. If you did, please like and subscribe, and I'll see you next time. Bye.